Hello there, my name is Dakshingole, and I am the CEO of Riptide, a non-profit organization dedicating to helping those in need of energy and reliable resources. Today I will be talking about our system design plans for our upcoming hydroelectric system dedicated to helping Indonesian farmers and homeowners. So here we have our little goal statement. And here it says that we strive to offer a cheap, low maintenance, and legal form of electricity to Indonesian homeowners. But you can read more about that on our website if you would like. The first thing I'm going to talk about is our design specifications. So when we select a product, right, we have to select from a range of products. Before we do that, we need to establish some guidelines that our products may be based off of. So let's start off. We have the first guideline is cost. The hydroelectric system should not exceed $500 because one of the Indonesian homeowners' requirements is that it should be cost effective. The hydroelectric system also should produce at least 30 kilowatts of electricity per day. And we said 30 kilowatts because the average home produces or requires around 28 kilowatts of electricity per day, and the client requires that they have sufficient power for the average home. Now, safety is also an interesting one. Here, the system must be in accordance with the laws of Java, Indonesia. See, with the Indonesian homeowners, they have to get their energy via legal means. So, therefore, we as Riptide establish a specification here stating that this source of electricity must be legal for them to obtain. Some more of our essential specifications include the sustainability for the customer, which is essentially the maintenance. The system should require a maximum of $1,000 of maintenance per year, which means like there's just a maintenance cap of $1,000. It shouldn't exceed that. And this is based on the client's requirements for having a low maintenance system that they could keep on. It's cheap in the long term, essentially. The next one is materials. The system should source at least 75% of its materials within areas in the region, such as junkyards. And this is based on the client's need for cost effectiveness, because if it costs a lot of money to make it, it costs even more for the client. And finally, we have sustainability for customer again. And this talks about how the system should function for a minimum of 10 years before it should be replaced by any means, because the Indonesian homeowners require a sustainable energy source that will last them a long time. And now here are some desired specifications. And these aren't necessary, it's just that we would like to have them. So the first one is environmental impact. The system shouldn't leave a carbon footprint greater than 5%. Now, this isn't a specification or something said by the client themselves, but it would be a nice addition, you know. And the size, this is also just for convenience. The system should be portable and relatively small with a maximum weight of 20 pounds. Now, this isn't something the client requires, but it would be a nice addition to have. Now, here are some feasible ideas we came up with from those specifications. And from these, we will choose one idea that will be our chosen one. So, the first idea, so how this works is the flowing water, it hits these little flaps right here, right? And that spins this turbine. And when the turbine spins, this metal cylinder right here also rotates along with it. And this metal cylinder is connected way up top to a generator. So the generator takes the kinetic energy from the spinning metal cylinder and it turns that into electrical energy. And that's the same concept for all of these turbine designs. So the second one here, instead of having flaps on the outside, it has little wings or cusps on the inside, And the idea is that the water would stay inside of these little areas for a bit longer and spin the turbine even faster to generate more electrical energy. And this is the final design. It's similar to the first one with the flaps, but instead it has more like fins, and this is my horrible shading, but it's meant to show that it's like a little pocket so that the water can go in and push it around. Yeah, now we have chosen a design, and that was sketch number 3, the one with the fins. So why did we choose this one? What did we base it off of? So we chose our designs based on how well they followed the specifications and which one followed the most of them, especially the essential specifications. So the main guideline that we had was that the system should not exceed a budget of $200. Yeah, $200. The chosen design, sketch 3, meets this specification because previous research has shown that the design only should cost $175. A man named Daniel Connell, he's an expert in renewable resources and making them affordable. He found a $50 version of a hydroelectric system that would produce around 8.5 kilowatts of electricity, and we obviously require 30 kilowatts of electricity. So we scaled that up, and in the end, the design would cost around $176, but this is significantly under the budget of $200, but it also doesn't take into account the material costs that won't be included because we're sourcing most of the materials from the junkyards nearby, which are for free. So this is actually much lower than the budget of 200 USD. And finally, we will be evaluating the success of this specification in the final design by looking by looking at all of our costs and everything, adding them all up, and making sure that they're under 200 USD. Now, the second specification that I meant was function, and that the system should produce at least 30 kilowatts of electricity. So the system mentioned the third design, right? It's based on another popular design for hydroelectric systems known as the Pelton model, and there's been lots of research done on this model, and most of it has shown that the average Pelton model turbine in a micro hydropower system will generate up to 100 kilowatts of electricity per day, which is way above the 30 kilowatt mark that we set. And we will address the success of this specification in the final models of design by doing a digital simulation, and we will measure the energy output in that simulation and compare it with the specification above. Our final essential specification that I meant, I'm not going to list all 6 of the essential specifications. These are just the main 3. Here we have the system should source at least 75% of the materials within the area in places such as junkyards. This meets the chosen design meets this specification because the design, as I said before, is known as the Pelton model, and this design is typically made out of metal or even plastic. And metal and plastic are materials that are readily available within junkyards and local areas. And so it clearly meets the specification. And we will evaluate the success of the specification by dividing the amount of materials we have by dividing the amount of materials we got from the junkyards in the local areas, and dividing that by the total amount of materials, including the ones that were purchased that we had to purchase. And if the percentage is above 75%, then the success criteria is met. And now I will be showing you a detailed model of the chosen design, which is sketch 3. So here we have a top view. You can see the extended fins I discussed before. So what happens, the water, let me get a laser pointer. So the water comes in through here, it pushes these fins around, spins them around really fast. That spins this main body of the turbine, which then spins the cylinder over here that's connected to the generator. and the kinetic energy from this thus goes into the generator to generate electrical energy. And it's the same idea so we have another angle right here. Here we have the same rotating body, the rotating metal cylinder, and the extended fins. Alright. And finally we have a horizontal view of this. We have the main rotating body right here, the extended fins right here, and the rotating cylinder as well. And this was all made using SketchUp, which is actually a really nice tool to use. I would recommend it. Yeah, thanks for watching. I hope you enjoyed. Make sure, yeah, that's it. Have a great day. Peace.